Oh, not on that. Not on that one. Broken. Slow. Come on. We are on 3.5. There we go. All right. Today is about graphing techniques, basically the transformations of a function. We're going to shift a function up, down, left, right. We're going to shrink it. We're going to stretch it. So all the transformations we'll learn today. So the first one is a vertical translation, meaning if any number k is added to the output of a function, this means that we will shift the function up k units or we will shift the function down k units. So it has to be added to the output of the function. So on the outside of the function. And vertical transformations, I'll tell you this, are straightforward. If it's plus k, you go up k. If it's minus k, you go down k. Horizontal transformations are going to be opposite. So we have a horizontal transformation if a number is added to the output of a function such as f of x minus h or f of x plus h. So if it's f of x minus h, this means the graph will be shifted to the right h units. If it's f of x plus h, this means the graph will be shifted to the left h units. So with horizontal transformations, always think opposite. So x minus h means we're going to the right h units. X plus h means we're going to the left h units. And now the definition of a parent function. A parent function is just the original function before any transformations have been applied. X, x squared, the square root of x, absolute value of x, whatever a function is without any transformations. Okay, with that being said, let's go ahead and practice vertical and horizontal shifts given the parent function of x squared. All right. And I'm going to do this by XY charts just so we see how it's numerically done, and then we'll plot everything on the graph. So first off, let's go ahead and graph x squared. So we'll start with the parent function. I'll call it A. We're going to say x and y equals x squared. This is our parent function. And I'm going to pick values that will only fit on our graph below. So I'm going to go from -3 to 3. And now all we're going to do here is square all these numbers. So we'll get 9, 4, 1, 0, 1, 4, 9. There's our parent function. Now, let's go ahead and make an XY chart for the first transformation we see. They give us a transformation of x squared plus 3. This is going to be a vertical shift up 3 units. So we're going to call this one B. So we're going to have x and y equals x squared plus 3. Okay. So what we're going to do now is we're going to stick with the original x values because since this is a vertical shift, it only affects your y values. So your x values will stay the same. And to make this real easy, well, one way you could do it is plug them into the function. Or another way to think of it is just take all these y values and add what to them?
3.
3. That's it. So you'd get 12, 7, 4, 3, 4, 7, 12. And there you go. We have just transformed the parent function just by shifting it up 3 units. So before we get into the next transformation, let's just go ahead and plot what we're looking at. So for the first function, the parent function, I'm at 0, 0, 1, 1, 2, 4, negative 1, negative 2, 4, 3, 9, negative 3, 9. So here's our parent function. Ah. And now we're going to graph our vertically transformed function. All we did was shift it up 3. Negative 3, 12 is not going to fit, but negative 2, 7 will. So 4, 5, 6, 7, right there, right there. And then negative 1, 4, there, there, and 0, 3. Okay, so you have x squared plus 3, and then we have x squared. Now let's graph the last transformation that they give us, which is x plus 3 squared. And this is going to be our horizontal shift, but which way?
Would it be to the left?
Good. So actually, I'm going to do this. X and y equals x plus 3 squared. So now you have a horizontal shift to the left. And once again, to do this, since it's a horizontal shift, this is going to affect all your x values. So what we can do is take the original parent function's values, and since it's a shift left 3 units, you are going to subtract what number from all the parent function's coordinates?
3.
3. So I'll get negative 3 minus 3. That gives me negative 6. And then negative 5. And then negative 4. And then negative 3. Negative 2. Negative 1 and 0. I'll make that fit a little better on here. There we go. And since it only affected the x values of the parent function, your y values are going to stay the same. So this means you'll get, let me clean this up, 9, 4, 1. Okay. 9, 4, 1, 0, 1, 4, and 9. Okay. And to show that transformation, we can plot it on the graph. And I'll be at negative 6 and negative 9. So it's that. That's 3, 4, 5, 6. So I think I'll be here. Negative 6, 9. And then negative 5 and 4. 3, 4, 5. Right there. Negative 4, 1. And then negative 3, 0. And then 4, 1. Oh, sorry, negative 2, 1. Negative 1 and 4. 1, 2, 3, 4. And then 0, 9. Let's see. Oh, negative 5, 4. That's not 4. Down here it is. There we go. And here is the graph of our horizontally shifted x squared function. So this one is x plus 3 squared. So this said shift left 3 units. And this one was shift up 3 units. And all we did there was transform the parent function. So those are what vertical shifts and horizontal shifts are. Any questions on that? All right, then. Then let's get into vertical stretches and horizontal stretches. So a vertical stretch happens if our function is multiplied by a positive number of a that is bigger than 1. So if our function, which is right here, if we multiply our function by some number bigger than 1, then we will vertically stretch all our y values. So that will be a vertical stretch. A horizontal stretch is if the inside of x is multiplied by a positive number a, but the only way it's going to be stretched is if the number is between 0 and 1. And for horizontal stretches, I always say think opposite. So whatever number is inside the function, you are always going to multiply by the reciprocal, 1 over a. So vertical transformations are straightforward. Whatever number times our function, we'll vertically stretch it. Horizontal stretches, whatever number is inside the function, you're going to multiply by the reciprocal. And it's a stretch if that number is between 0 and 1. So horizontal stretches, I just say always think opposite. Okay, so let's go ahead and try our stretches out by manipulating the parent function, the square root of x. So once again, we'll just do this by xy charts. So a will be our parent function, y equals the square root of x, and I'll choose numbers for the square root of x that'll fit on our graph, 0, 1, 4, 9, 16. And just square root all those numbers, and we'll get 0, 1, 2, 3, 4. Okay, so there's our parent function's coordinates. And now we want to deal with the transformation of the parent function. And now this is 2 times the square root of x. So what type of stretch is this going to be? Vertical or horizontal? Is there anybody alive out there?
Vertical?
Vertical, good. Which means verticals only affect your y values, which means our x values are going to stay the same, and we're going to multiply all our y values by what number?
2?
2. There you go. And I'm just going to rewrite it a little differently this time to show the transformations. And I'm going to say 2 times y. This will just show us the transformations. So our x values stay the same, 0, 1, 4, 9, 16. And I'm going to take all those parent function y values and multiply them by 2. So you'll get 0, 2, 4, 6, 8. And there you go. There is the vertically stretched 2 square root of x, or square root of x. So this is a vertical stretch by 2. Okay. And like I said, before we continue on, let's go ahead and graph what we have. So I'll graph the parent function. Doesn't have to be chat. You can just respond. Dead chat. What's everybody watching tonight? instead of lecture. Four, 2, and then 9 and 3. Here's the square root of x. And then we do the stretch. And we got 0, 0, 1, 2, 4, 4, 1, 2, 3, 4, and 9, 6. 3, 4, 5, 6. There we go. And here's our vertically stretched graph by 2 units. Okay. And then the next one, again, we have h of x equals the square root of 1/2 x. So with that, create my xy chart again, but I'll rewrite it. H of x equals the square root of 1/2 x. So now the number inside is between 0 and 1, which means that this is going to be a horizontal stretch. But remember, for horizontal transformations, we always think opposite. So if there's a 1/2 in there, we are going to multiply all our x values by what number?
Is it 2?
2. Good. By 2. Because no matter what number's inside, you're always going to multiply by the reciprocal. Which means I'm going to rewrite it to show the transformations. It's going to be 2 times x, and our y values will stay the same. So from the above, you are just going to take the parent function's x values and multiply them all by 2. So 0, 2, 8, 18, and 32. And then your y values will stay the same. 0, 1, 2, 3, 4. There we go. And now we can graph. So zoom in a bit. There we go. And then 0, 0, 2, 1, 8, 2. And then the others won't fit. 18 and 3, 32 and 4. And there it is, guys. Those are vertical stretches and horizontal stretches. Any questions on that page? All right, then. All right. So if we have vertical stretches and horizontal stretches, then we can also have vertical compressions and horizontal compressions. So for a vertical compression, if the output of the function is multiplied by a number between 0 and 1, once again seen here and here, if a times f of x, where a is between 0 and 1, this will be considered a vertical compression. We take all those y values and we shrink them. And now for a horizontal compression, well, the inside of the function, f of a of x, f of a times x, if this number is bigger than 1, then it's considered a horizontal compression. And just like the horizontal stretch, whatever number's inside that function, you are always going to multiply by the reciprocal. So always multiply by the reciprocal. All right. So those are vertical and horizontal compressions. And once again, let's try it out. So now we are given the parent function of the absolute value of x. Again, x, y charts to show the transformations. So a is my parent function, and I'll have x and y equals the absolute value of x. And I should choose, let's see, I'll go from -3. That should be enough information. -3, -2, -1, 0, 1, 2, 3. And for the absolute value function, we know if you plug in any negative number, it's going to come out what?
Positive.
Positive. And if you plug in any positive number, it's going to come out
The same.
the same. Good. There we go. There's our parent function's coordinates from -3 to 3. Pick more points if you want, right? But now, let's go ahead and make a chart for our transformation. So B is g of x equals 1/2 times the absolute value of x. So since this number is on the outside of the function and it's between 0 and 1, this is going to be a vertical compression by 1/2. So to show the transformation, again, since this is only a vertical transformation, it only affects the y values. So we're going to multiply all the y values by what number?
Two.
Well, vertical transformations
Yeah.
are straightforward. So it's going to be multiplied by 1/2. Okay. And your x values stay the same, -3, -2, -1, 0, 1, 2, 3. Take all these y values and multiply them by 1/2. So 3/2, 1, 1/2, 0, 1/2, 1, and 3/2. There we go. And again, let's go ahead and graph what we have. So for the absolute value function, 0, 0, 1, 1, 2, 2, 3, 3. It'll keep going up that way. And then -1, 1, -2, 2, -3, 3. And our absolute value would look like this. I could draw a straight line on the computer to save my life. There we go. There's the absolute value of x. Now let's go ahead and graph the vertically compressed absolute value of x. And you'd be at -3 and 3/2, which is 1.5. So right here. And then -2 and 1, -1 and 1/2, 0, 0, 1 and 1/2, 2, 1, and then 3 and 1/2. There we go. What we've done is taken all our y values and vertically compressed them. We have shrunk them by a factor of 1/2. Okay. And then the next transformation is going to be our compression. H of x equals the absolute value of 2x. So let me write that here. C, the absolute value of 2x. All right. And this one will be the horizontal compression by what factor?
Would it be a 2?
Remember, if it's horizontal, you always think opposite. So whatever number is inside the function is going to be the reciprocal. So what would that be?
1/2.
1/2. There we go. And to show the transformations, you're going to do 1/2 times x. Your y values will stay the same. And we are just going to take all the parent functions, x values, and multiply them by 1/2. So -3/2, -1, -1/2, 0, 1/2, 1 3/2. There we go. And I'll shrink this in a second because your y values stay the same. So 3, 2, 1, 0, 1, 2, 3. There we go. That's probably good for now. Okay, cool. So let's go ahead and graph what we have. And for this one, -1.5. So 1 and 3, 1, 2, 3 will be right here. -1 and 2, -1/2 and 1, 0, 0, 1/2, 1, 1, 2, and then 1.5 and 3. So our horizontally stretched absolute value of x looks like this. There we go. And here is the absolute value of 2x. All right. So again, remember with horizontal transformations, always think opposite. X plus a number, you shift left. X minus a number, you shift right. Horizontal compression and horizontal stretch, for those ones, all you have to think about is whatever number is inside, multiply by the reciprocal. But any questions on this page?
Hey, hang on. I don't have a question, just writing still.
Okay. No, take your time.
Okay.
All right. Let's do it. All right. The last of the transformations. Okay. are reflections. So we'll have a reflection about the x-axis if the output of a function, if the outside of a function is multiplied by -1. So if we have -1 times f of x, this will reflect over the x-axis. And then a reflection about the y-axis, if we have the inside of the function multiplied by -1, then this will be a reflection about the y-axis. So outside of a function, it's going to be over the x-axis. Inside of the function, you reflect over the y-axis. All right. Let's try it out with the square root of x again. Why not? There's our parent function. So for a, we'll just have x and y equals the square root of x. And we already know what numbers to pick. 0, 1, 4, 9. I don't need 16. And you square root those, and 0, 1, 2, 3. All right. And now we're going to start with our reflection over the x-axis because the negative's on the outside. So b, we're going to use g of x equals the negative square root of x. And since we're reflecting over the x-axis, it's another type of vertical transformation because we're changing the values of the y's. So this means that all we have to do is take the original y values from the parent function and multiply them by what number?
-1.
-1. So I'm going to say -1 times y. So the x values stay the same, but now you'll get 0, -1, -2, -3. There we go. And let's see what that looks like right now. Let's go ahead and graph what we have. So here you'll have 0, 0, 1, 1, 4, 2, and then 9, 3. There's the square root of x. And then 0, 0, 1, -1, 4, -2, and 9, -3. No. And here we get the negative square root of x. So you see we have reflected the original parent function. We've reflected it over the x-axis. Okay. And then the last one to deal with, h of x equals the square root of -x. This would be reflect over x-axis. And the next would be reflect over the y-axis. And since we're reflecting over the y-axis, we're changing the signs of the x values. So this time, we're going to take the parent function's x values, and this time we're going to multiply them by what number? Anybody? -1. Oh, I see it in the chat. Perfect. All right. -1 times x, and your y values will stay the same. And you'll get 0, -1, -4, -9. And your y values stay the same, 0, 1, 2, and 3. All right. Now plot what we have, and we'll see the transformation. 0, 0, -1, 1, 1, 2, 3, 4, -4, 2, and -9, 3. There you go. And here's the square root of -x, which reflects over the y-axis.
That one confuses me, and I don't know why.
Which one?
The
Both?
the last one.
So since it just reflects over the y-axis, you're doing a change of signs for the x values only, right?
Uh-huh.
So you've taken these x values and you're changing them from positive to what?
Negative.
Negative. So they're coming over here, right? So also, if you're thinking in terms of a negative number in the square root, well, when I plug -1 in, there's already a negative there. So the number is going to become what?
There we go. That's what was messing me up.
Maybe that's what was getting you.
That's what it was.
And remember, you can always check your transformations to see if you're doing it right by plugging the number in. So let's say I wanted to check -4. I'd say h of -4, and I'd get the square root of negative times -4, which would give me the square root of +4, which would give me 2. So this checks with those 2 points. Does that make sense?
Yes, that makes sense. I forgot about that little negative sign.
There you go. Yeah. It's the only time we can plug negatives in and get an answer from. Okay. Those are transformations. So we did shifts up and down, shifts left and right. We did stretches, we did compressions, and then we did reflections. So any questions on those? Maybe you're like, I learned these in high school. I got this. Maybe you're the ones who the teacher taught, just put your finger on the graph and move your finger up. And there you go. There's your transformation. All right. Well then, let's move on to something more fun then, such as completing the square. Yeehaw. So here we are completing the square on a function. The reason we're doing this is so we can graph this function by the use of transformation. So my brain was too scrambled. Too much SpongeBob. All right. Okay. So remember, if we're going to complete the square, and we'll keep this simple, right? So to complete the square, we need to take half of the middle term's coefficient. So here I'll say complete the square. And also, one thing to note about completing the square is that your function must be in this form: ax squared plus bx plus c. So our function must have a leading coefficient of 1. If it doesn't have a leading coefficient of 1, then we have to do some factoring. We have to fix it in order to get a coefficient of 1. Okay, so what we notice is that the function given is in that form. And when I say that form, I mean the leading coefficient of our function is 1. So now, when we complete the square, we take half of the middle term's coefficient. So we are going to do, let's see, what's the best way to put it? Yeah, complete the square, we have the form, and then we're going to do b over 2 and square it. So we're going to take half of the middle term's coefficient and square it. So from our problem above, we have -8 over 2 squared. This will give me -4 squared, which will give me 16. Okay. And now what we're going to do with that number is take 16 and add it and subtract it on the same line. So I'll show you our rewrite. So now this becomes f of x equals x squared minus 8x. And now I'm going to have plus 16 minus 16 plus the 1 that was already there. So what we're really dealing with is, what is 16 minus 16?
0.
0, right? So we're dealing with like a manipulation by 0, which is crazy, right? So when we do this manipulation, this completing the square, after you do the completing the square process, this trinomial becomes factorable because this is now a perfect square trinomial. So this is now factorable. Oh, and I guess I should put add, subtract 16. There we go. Okay, so now we are going to factor x squared minus 8x plus 16. What does that factor to?
X minus 4.
Good. X minus 4 times x minus 4. And then the negative 16 plus 1 is going to give me what?
Minus 15.
Minus 15. Good. And now all we have left to do is just simplify it, and we will get x minus 4 squared minus 15. And what you have just completed is taking a quadratic function, you're taking it in standard form, and by completing the square, you're putting it into a form called the vertex form. But we won't touch on that until the next lecture. For now, we are just graphing by transformations. And if we graph this by transformations, well, what are the transformations you guys see? What is the x minus 4?
So we're going to the right 4 and then down 15.
That's it. This is a horizontal shift, right 4 units. And this is a vertical shift down 15 units. Well, if we are doing transformations, what was the parent function?
X squared.
X squared, right? So if we just made our quick parent function XY chart, and I'm just going to go from -2 to 2, why not, just make it simple. That'd be 4, 1, 0, 1, 4. And if we transform it from our function above, if that horizontal shift to the right by 4 units, what are you going to add to all your x values?
Four.
4. And then what are you going to subtract from all your y values?
$15.
15. There we go. So we're just going to transform the parent function. I'm going to add 4 to all those x values on the left. And I'll get 2, 3, 4, 5, 6. And then I'm going to subtract 15. 4 minus 15, what's that? Negative 11. And then 1 minus 15, negative 14. And then minus 15, and then it should go back to minus 14, minus 11. Okay. So to graph this function, let's just do this by, I'll just say I can make my y values by 3 since 15, we don't have a negative 15. So let's just say that I can 3,
Negative
6,
15's right there in the middle.
9, 12, 15. What? And then there's 0. And then my x values can stay the same. So I'll have 2 and negative 11, which we'll just put around here. And then 3 and negative 14, which I'll put around here. And then I have 4 and negative 15, and then there we go. And there it is. Because if we drew our x squared function, this is what it would look like. And all we did was shift it to the right 4 units. So we went to the right 4 units and down 15. All right. So any questions on that process, including the completing the square process? Man, everybody's got this, huh?
With the middle term, the B term, you said that only worked if what with the A term? If it was 1 or greater?
So in order to complete the square, the leading term on your function has to be 1.
Okay.
It has to be 1. If it's not, we have to fix it.
Got it.
Which will lead us to the next one. Hey, Carl, you want to do something?
Yeah.
All right. You
You
get the
go.
last one of the day.
Sweet. Let's see if I still have your I can go to
Oh, boy.
history.
All right.
Nah, I haven't saved in my history. Hmm. Oh, no.
No?
I don't. Let me see.
Oh, good.
It will. Hold on. It was this time on Wednesday. I've used the internet a lot since then, but I can get there. Okay, that's going to take forever. Just link it to me.
There you go. There you go. Just to you. Paste. Bam. There you go. All right.
All right, let me close these other incriminating tabs and share my screen. Uh-oh. This is 3.5.
Yeah, 3.5.
2021 edition.
Last page. I didn't put 2021 this time. I should. Yeehaw.
Lettuce. Lechuga ver. Here we go. All right.
There we go.
Okie dokie. Color I want. Regular blue's fine. Oh no. Oh, that was the highlighter anyway. My bad. Make sure my lines are thin. All right. So I'm going to rewrite this as, now check this out. Remember that Professor Carrillo said that we want this leading term to be 2, right? Or to be 1. But I don't want to divide 2 off this 19 because that's lame. So I'm going to rewrite it like this. And that's totally fair. Like, this is completely legal mathematics. So now I can rewrite f of x like this. And now I've got just this x squared minus 6 to complete the square on. I'm going to leave this 19 alone. So remember, c is equal to the b term divided by 2 squared. And in this case, b equals -6. So then c will be equal to -6 divided by 2 squared, which is equal to -3 squared, and that's equal to 9. So then we get f of x is equal to 2 times the quantity x squared minus 6x plus 9 minus 9 inside the set of parentheses plus 19. You want to make sure that you rewrite your plus and minus 9 inside the set of parentheses, because you want to do this as a trick to remind yourself that when you move this 9 outside, this -9, you have to multiply it by the 2 up front. Whatever you factored off, you have to multiply that negative term of your added 0 by that. So then this will be equal to 2 times x squared minus 6x plus 9 minus 18 plus 19. And that is equal to 2 times x minus 3 squared plus 1. Little hint, I don't know if Professor Carrillo said this, I think he did, but this number right here will always be the number that goes in here at the end.
Ooh, I didn't say it, but yes, good job.
Yes. Help remind you guys. So this is what we're going to work with then. We have our final answer will be, for what we're working with, will be f of x is equal to 2 times x minus 3 squared plus 1. Now this is how I normally do these. This is what I'm going to say. I'm going to label my axes 1, 2, 3, 4, 5 on the horizontal, and then I'm going to label the vertical -2, -4, -6, -8, -10. And I hope Professor Carrillo is smart enough to understand that when you label it on just one side, you mean that for all the other sides.
Yeah.
And then that will let me come in here and say, well, I know that I'm going 3 to the right and 1 up. from this transformation. And now that I've adjusted this, there's two reasons why I'd scaled my y-axis by 2. I know that, one, I'm going to run out of space real fast because these numbers are going to be squared at the end, so my results will get real big. But also, since this is being multiplied by 2 and I scaled my y-axis by 2, I can just make this shape the original shape of a regular x squared graph now, and it'll match. And since I basically have these memorized, I don't even have to know what the numbers are. I know that when I go 1 over from, in either direction, I'll go up 1. When I go 2 over, I'll go up 4. Actually, I may have put those, may have counted too many there. I think I counted too many there.
I
I'll
thought
go
your
up
Y's were 2s.
1, 2, 3.
Yeah.
They are. But because I scaled it by 2, I'm just doing the original numbers from x squared. You guys see how that? I'll write it out so it makes more sense what I'm saying here. So my original one, y equals x squared, right?
I think
What
what
the
you're trying to
trans-
say though
What the transformation
is,
would be like
yeah.
this, right?
Yeah, if x equals 3, y would be 1, but you have it on 2 if your y scales are 2 apiece. I was giving you a hard time. I know what you're saying.
Okay.
Well, make the XY charts anyway. It's good to
Okay.
see the visual, the numerical visual.
Right. So then if I do my next transformation, that'll be x, and then what's the best way to do these? You want to do reverse PEMDAS, right? So it'll be, we'll take our last result and just add 1 to it. So then that gives us 10, 5, 2, 0, 2, 5, and 10. And then we want to do,
Hey, if you're doing PEMDAS, why don't you multiply by 2 first and then add 1?
no, you do reverse PEMDAS.
Oh, you're doing reverse PEMDAS. How
Yeah, I
dare
thought
you.
that's the way you usually do them, right?
Well, I would have just, on that XY chart you just made, I would have added 3 to all the X values,
Mm-hmm.
and then I would have just done 2 times Y plus 1.
Gotcha. Okay. Yeah, I guess that's
that
the
sums
easiest
it
way.
all up instead of having to make multiple XY charts.
Delete. Okay, there we go. If you want to do it all in one step, you can. So then this would be 0, 1, 2, 3, 4, 5, and 6. And then it's 2 times this plus 1. So that's 19, 9, 3, 0, 1. Just kidding. Got to add 1. 1. And then what would that be?
You just repeat again
It just
after that, right?
repeats 3, 9, 19.
There you go.
Cool. And if we go over here and we take a look at the graph that I drew, put my lines on there, see if I can do this. I'll just miss 1 point completely. Pretend that those connect properly. Since this is scaled, I may have gone too far with these points. Oh no, I went too far with these points. I counted too much. I got too far ahead of myself. I had to go down 1. There we go.
Well, your 2 should be on 3, but it's on 4 on your scale, but whatever.
What? What are you talking about?
Because your scale goes by 2s, right?
Mm-hmm.
So when X is 2, you have it on 4.
Oh yeah, I see what you're saying. Mhm. I got ahead of myself, guys. The real problem is I started, should start halfway up here at 1,
There you
and
go.
then it goes like this, 3, and then it's got to go
It's
to
just going to
what,
be between
9?
all your numbers, right?
Hell yeah, buddy. That's okay. And we'll go like, wait, Or should it go up one more?
No, you have
No,
9.
19.
Yeah, because
Nope,
you're
yeah,
doing
it's
it by
gotta go up one
2,
more.
so you're
Yeah,
good.
it's gotta go
You
up
got
one
it.
more. Gotta go up one more. Hell yeah. There you go. And
Now it's fixed.
that's-
There we go.
Yeah.
All right. And complete.
Yeah. So it can save you time if you bother to draw your graph correctly in the first place. But yeah,
All right.
that's it.
Any questions on that, including the completing the square process?
I'll take that as a no.
All right. Well, other than that, we are done. So if you got questions, stick around. If not, we'll see you on Monday.